Okay, so any questions before we get started? So we have 11 questions to go through today. Okay, so I guess we're going to actually doing this relatively fast. Okay, and next Tuesday and next Thursday we still have lectures. We are going to enter in chapter 13. Okay, I will go slow on next week's lecture, but trying to attend if you can. All right. Okay, so today we're going to go through the questions for chapter 11 and 12. Okay, so these are the things that we need to actually memorize. Okay. So this is actually the first type of question we want to go through today for chapter 11. So it's basically, you're all going to see this big table, okay, and trying to figure out the orders of your reactants. Okay, so very standard type of questions. So question says, in the experiment on the reaction 2ICl gas plus H2 gas, they give you I2 gas plus 2HCl gas. And then you have a table tell you how the reaction rate will change with different initial reactant concentration. Okay, so every time you see these sort of questions, you want to know who are your reactants. So that's always the first thing you want to see from this equation. Because you know your rate law will have a form like this. Rate equals rate constant K times your reactant to certain power. Right. So every time you see that equation, you know that's actually where you're going to get started. Okay. Once you have that in mind, the next thing you do is really to, okay, the Q is trying to figure out your X and Y, right? And then we know the X and Y can be any number between 0 to any integer, right? Well, not necessarily integer, any numbers. Okay. So the way you do it is you write out all this red law based on the given data, right? So the first one, you will be write out the rate. Initial rate is 3.7 times 10 to the negative 7 is equals to rate constant K times ICL concentration. In this case is 1.5 to the X power, H2 concentration 1.5 to the Y power. That's how you write your first equation. And you repeat the same process for your equation 2 and 3. So you are going to get 15 times 10 to the negative 7 equals to K times 3.0 X power 1.5 Y power. And then equation number 3 will be 134 times 10 to the negative 7 equals to constant K times 3.0 to the X power 4.5 to the Y power. Okay. And then you're going to use these three equations to solve your X and Y. And the way you do it is you do these equation divisions. Okay. If you want to solve, they say you want to solve X first, then the two equations you pick is that the concentration of your first reactant need to be different, but the other one need to be the same. Okay, so one is different is actually one is 1.5. The second equation is actually 3 for your ICL, right? But for your the other reactant H2, they are actually the same. So pick these two first. Then you do your equation 2 over equation 1. Then you're going to get this divided by that. They will give you a value around 4. K divided by K, that's 1. Okay, 3 divided by 1.5, that's 2 to the X power. And 1.5 by 1.5 is actually 1 to the Y power. Okay, so by doing this, you should be able to figure out that X is going to equal to 2. Okay, so you must get yourself familiar with all these calculations, right? So once you figure it out, then the things next is actually trying to figure out the Y. And to figure out Y, I try to keep the first term the same, but the second term different, right? So I do equation 3 over equation 2. Then I'm going to get this divided by that, that's 9, roughly. Okay. This equals to K divided by K is 1. 3.0 to the X power, that's 1 to the X power, and then this will be 3 to the Y power. Therefore, you know Y equals 2. Okay, so once you solve this, then you will know the reaction rate will equals rate constant K times ICL to the second power H2 to the second power. Okay, so overall it's actually a fourth order reaction. Okay. So let's how you solve this type of question. Okay, and the potential question you will be asked is actually, can you actually solve for K, right? So let's say you want to solve for K. Then what you need to do is actually just plug in the values from either equation 1, 2, or 3. It doesn't really matter. It will give you the same K. Okay, so let's say I use the value from equation 1. Therefore, I know I can write 3.7 times 10 to the negative 7 equals to the constant K times 1.5 to the second power, 1.5 to the second power for your H2 as well. Okay, so by doing this, you'll be able to solve your K, which is going to equals to 3.7 times 10 to the negative 7 divided by 1.5. 1.5 square. Okay, so you'll be able to get a number equals to 7.31 times 10 to the negative 8. Okay, so that's all the variable you have in this red law, right? Your rate constant K, and then the two orders for your two reactants. Okay, so this is actually a very standard type of question, and you will, I believe you will actually have one in your midterms. So make sure you understand the logic, how you can actually get these orders for your reactant quickly. All right, any question for this? If not, then let's go to the question number 9. Okay, so question number 9 says, what would be a red law for the proposed mechanism below? Okay, so you see 3 steps, and it labels first step slow, second step fast, and third step fast, right? So in order to solve this one, the first thing you need to do, first is that every time you see this kind of setup, right, it is a very typical standard elementary step type of questions. Okay, so the first thing to actually figure out is actually what is your reactants, because so you know your final red law should only contains reactants. Okay, so how do we actually know the reactants? You add everything up. Okay, so if you add up all the steps, what do you have? On the left will be I2 plus I plus H2 plus H2I plus I. On the right, you have 2I plus H2I plus 2HI. Right, I just add up everything. And I start to actually cancel out the things that show on both sides. So you have 2I, 1I, okay. And then H2I, H2I cancels out, right? So the only thing that remains is I2 plus H2. They give you 2HI. Okay, so let's actually the overall reaction. Therefore, you know your red law will look like something like this. Rate equals to K times I2 x power H2 y's power. Okay, so let's actually the basic format that you're going to have. And from here, you should also understand that you don't need all the reactant to show up, right? The things that you want to have actually the red law you derive must only contain your reactants, because the x and y could potentially be 0, right? If it's 0, it means actually the reactant will disappear in your final red law. Okay. So once you have these things in mind, the next thing is actually go to the slow step and write out the red law directly based on the elementary step, right? So if you check out this, that is actually your slow step. Therefore, you know you can write out the rate equal to rate constant K. Okay, so just to distinguish that I'm using the K is actually K for that first equation, first elementary step, I use K1, okay? Reactant is your I2. Okay, so that's actually the reaction for these specific steps, right? So you will be able to write out a rate very low like this. Okay, so once you get this red law, what do? You are going to check, does the red law you write out based on your slow step only contain the reactant? Okay, if it only contains your reactant, you're done. Okay, so in this case, do you have only reactants derived from the slow step? Yes, right? And that's it. It's end of the calculation. Very simple. Okay, what if it's not? Yes, they need to actually replace all those non-reactant species using other equations, just like how we do it in the chapter 11 examples. Okay, so make sure you understand this concept. Okay, if you're not very familiar with the things I say, go back and rewatch the video when we talk about more complicated case in chapter 11. Okay, so this is actually how you solve these questions. Okay, next one. The reaction A become B plus C is second order in A. Okay, when the initial A concentration equals 0.1, the reaction is 20% complete in 26.2 minutes. Calculate the value of the rate constant K. What's the keyword here? Do you see the time? So it is what? Integrated rate law, right? What's the order of that? Second order, right? Therefore, you know the equation you will use is what? Right? There will be the equation you're going to use. Okay. So you need to practice this, right? So you see the keywords. Every time you see the time, integrated rate law, then looking for the orders. Second order, very straightforward. Okay, so that will be actually the plane you're going to use. Okay, so then do your QT pay, right? What's a Q? You want to solve for your K, right? Data that you have. The initial A means your A0 equals to 0.100 M. Okay, T is 26.2 minutes. Okay, what else do you have? Okay, so there's actually things, a sentence like this. I want to highlight this. So it says the reaction is 20% complete, right? So let complete, okay, highlight this word. If you look at the equation we're going to use, the AT is the remaining A, okay? And the reaction is what? The reaction is actually the decomposition of A, right? It says 20% decomposed. Okay, but you don't want the decomposed one, you want the remaining one. Okay, so that one is actually telling you this is 80% of the original concentration, right? So that you know your AT is 0.08 M. Okay, so this is actually the part that the student always have some difficulty to write it out, okay? Because that's actually the last piece you need. Okay, so you need to pay very close attention to the word, okay? If it says it's complete, okay, you know that's not the number you can use directly because the information you're looking for is actually the remaining A. Okay, so pay attention to this. Okay. Well, if you can actually get all this data properly, right? Then the things become very simple because you know equation is 1 over AT is just 1 over 0.08. K is the things you want to actually solve. T is 26.2. And then 1 over A0 is actually 0.1. Okay, so it becomes a very simple equation to solve. If you do that, then you can get a K of 9.54 times 10 to the negative 2 per minute. Okay, so that's actually how you solve this. Okay, but again, the keyword is actually you need to know, you want to see that there's actually a time component over there. Therefore, you know it's actually integrated rate law. Okay, then you know it's second order, therefore you know what equation to use. Then start to actually read the questions, digest your data, okay, and then write down the data properly. Okay, so complete is not the word that you want to have, right? The word you want to have is actually how many remains. Okay, so make sure you understand those little things. All right, any question for this? The equation is only for the remaining. So you need to actually have a clear understanding that what is actual things you can really use, right? So sometimes they play around with all these wordings. Okay, so you want to make sure that you know what the wording means. Okay. Number 11. This question says the food spoils about 30 times more rapidly at 25 degrees C than it is held at 4 degrees C. What's the overall activation energy of the process? Are the keywords. Okay, activation energy. So every time you see activation energy, there are only two equations, right? The first equation is A is A times exponential negative EA over RT. That's the first equation, right? Second equation will be natural log K1 over K2 equals to EA over R, 1 over T2 minus 1 over T1, right? So those are, every time you see this activation energy, you know, you will use one of these equation already. Okay? Then what? You need to decide which one to use. Which one? Second one, how do you know? At two temperature, right? You see how easy you can actually solve this problem? If you actually really see the keyword, if you memorize the things I asked you to memorize, this is actually a super easy question to answer. Okay? So this is indeed the equation you want to use, right? So now we actually can do our QD pair, right? What's the things you need to calculate? EA, right? Okay, let's look at the data that we have. How are you going to write this? You have two temperatures, right? One is 4 degrees C. One is 25 degrees C. Right? So you have T2 and T1 already. Okay. How about your K2 and K1? How are you going to write that? How I'm going to write that? Okay, so which one is actually faster? 4 degrees C or 25 degrees C? 25 degrees C, right? So you can say I have K1 at 4 degrees C. How am I going to write the K for the 25 degrees C? Yes, 30 times K1, right? Can you translate that? There's also something that's not very clear. Okay, if just read the questions, you may not necessarily actually write all things out. Okay, but that's the reason we're actually talking about these things here, right? So you know, you say, okay, at different temperatures, one is actually how many times faster, right? You can just assume the slow one as K1. Then your K2 will be just that much times faster. Just put the coefficient in front of like K1. Okay? The other thing that we need to know is that when we do the calculation, can you use degree C? You cannot, right? So into convert to K, right? Plus 273, that give you 277. This one will give you 298. Okay. Okay. What's the R you should use? Hmm? Yes, 8.314. How do you know it's 8.314, not the other? Yeah, it's not gas. It's actually all very simple, right? Some simple concept, if you understand it, then you won't confuse yourself. All right? So once you have all this information, then you can just plug everything in, right? Natural log K1, K2 is 30 times of K1 equals to EA over 8.314. Okay. T2 is 298. T1 is 277. Okay, so K1 will cancels out. Okay, therefore you end up with natural log 1/30 equals to EA over 8.314 times 1/298 minus 1/277. Okay, so the only thing unknown is actually your EA. Therefore, you can actually enter all these numbers in your calculators. Then you should be able to get the EA is going to equals to 1.11 times 10 to the 5th power joules per mole. Okay, so let's actually how you solve this type of questions. Okay, any questions so far? Is X for the KJ? Yeah, then divide by 1,000. Then that should be the answer. Okay. All right, so let's actually how you solve this activation energy type of questions. It's very standard, okay? Next one, which will be the reasonable unit for the rate constant of a second order reaction. So this actually tests the unit of K, okay? So previous I give you this equation, right? The unit of K is equals to concentration 1 minus n times the second, right? The n is actually the order of the reaction. Okay, so second order. Therefore, n equals to 2. Therefore, the unit of K will have concentration 1 minus 2 per second. And then they will give you n minus 1, s minus 1. And then apparently they don't use the molarity, right? So they use moles and liter. It will be moles per liter, -1, s -1. And then they will give you liter per mole per second. And there will be the unit. Okay, so make sure you know how to actually do this operation. So this, there's actually a lot of things can be asked for these figures. Okay, so we're going to go through all the possible questions that's related to these specific figures. Okay. So this question says, which later correspond to the transition states for the mechanism of the reaction depicted in the figures? Okay, so we have A, B, C, D, E, right? So what are the transition states? B and D, okay? The pigs represent the transition state, okay? Okay. What's C? Okay. What's A? What's E? Okay. You want to make sure you know every single thing I asked now. Okay. Next question. Is this reaction endothermic or exothermic? Exothermic. How do you know it's exothermic? Because the energy of your product is lower than the energy of your reactant, right? And those energy will be released to your environment. Okay, therefore it's a exothermic reaction. Okay, so okay, will the temperature of the solution increase or decrease? Increase. Okay. Next questions. Where is the activation energy? To D to where? D to A. Okay, you must know that. Okay. One more questions. How many steps? How many elementary steps should be included in this specific reaction? 2 steps. Okay. Okay. One more questions. What is actually the parameters can be influenced, or which peaks can be influenced by the catalyst? Okay, so catalyst only influence what? Activation energy. So it will be D. Okay. Do you actually memorize every single thing I say? You see how many questions can be asked from these figures? Yeah, we pretty much list all questions you can encounter. All right. Yeah, I think that's all. Okay, so make sure you know exactly what the potential question can come out from this specific plot. Okay. Yeah, so I think that's pretty much all the questions for chapter 11. Okay, so any questions though? We actually went through quite quickly, right? Because I'm afraid I cannot finish every single question today. So I go a little bit faster today. Okay, but so far, okay, we actually point out all the key questions from chapter 11. Okay, some of the questions actually not as deep as the one we went through when we have this in-person lectures in chapter 11. Okay, but do go back and watch those questions as well, because those are also questions from the midterms. Okay, so every single question we go through in the in-person lecture, they were the questions, okay, provided by the students. That means actually they were the midterm questions. Okay, so you want to actually make sure you understand how to do those more challenging ones in the previous lectures as well. Okay. Now we will go to a couple more questions for chapter 12. Okay, the first one. This says the water gas shifts reaction is extremely important one in the industry. Okay, so this one, CO gas plus H2O gas, they give you CO2 gas plus H2 gas. At a given temperature, the Kp, the equilibrium constant, equals 2.7. If 0.13 mole of CO, 0.56 mole of H2, 0.62 moles of CO2, and 0.43 mole of H2 are placed in a 2-liter flask, then predict how the reaction is going to move. Okay? So every time you see these things asked to predict how the reaction is going to move, Okay, either move to the left or move to the right. Okay, so it's a very, very standard Q versus K comparison. Okay, so remember this. If you see this apparently is actually a the multi-choice type questions. Okay, so it's going to give you a multiple choice. Okay, but in each choice, it's going to tell you, okay, the direction move to the left or move to the right, right? So, and it give you a bunch of numbers. Okay, so it's very standard type of question, right? You want to compare the Q and K. Okay, so if it's actually the question actually compare Q and K, it's actually very simple. You only have two situations, right? If your Q larger than K, direction will move to the which side? Reactant side or product side? Reactant side, right? Your Q is actually your current status. K is equilibrium, right? If you have Q is larger than K, means actually you have too much product than the equilibrium. Therefore, it will move to the reactant side, right? So you know if this is true, then it will move to the left, right? If that is true, it will move to the right. Okay, so these are the only two possible answers. Okay, if you see a question says Q larger than K, but move to the product side, it cannot be true. Okay, similarly, if it says Q smaller than K, it's going to move to the reactant side, right? But it says move to, sorry, Q smaller than K, then it should move to the product side. But if in the choice it says move to the reactant side, then they cannot be the answer either. Okay, so these are the only two possible answers. Okay. So if you have this in mind, the next thing you want to know is actually just want to know, okay, which one is bigger, right? Q is larger or K is larger? Because once you know which one, then you know the answer already. Okay. Now, how to actually figure out that, right? So you need to actually look at your data, right? The data is, you know, the reaction is CO gas plus H2O gas. That give you CO2 gas plus H2 gas. Okay. For this specific reaction, how do you calculate your Q? How do you calculate your Q? What did you write? On the top will be your product is CO2, right? Okay, so CO2 to the first power, right? And then H2 first power. Reactant is CO H2O. Should I put H2O? Yes or no? It's gas form, right? So you must put H2O there. Okay. When should you actually exclude the H2O? When it's actually in the liquid form. Okay, so be careful about that. Okay. So once you know how to write that, right, the next thing is actually you want to write your ice table so that you know where the number that's given should be placed, right? Okay. So where should I put this, that? Where should I put that? Which row? ICOE. You need to answer this one. I mean, I won't be there, right? So you need to actually answer this one for yourself, right? Which row should you put? I, how do you know it's I? What other words tell you it is actually I? Yes, place in the flask, right? Meaning that the reaction haven't started yet. Okay. Therefore, you know you should put 0.13 for your CO, 0.56, 0.62, 0.43. Okay. But let's actually the moles, right? But what you need is actually either concentration or pressure. Okay, so what do? You divide it by, why should you divide by 2? Do you see that? That's the volume of your container, right? And all plane is actually gas molecules. Therefore, the concentration again is more over the volume. Okay, that's why you need to divide it by 2. Okay. Since everything is actually in the row I, right? So if you plug all this number into this, you actually calculate your Q, right? So your Q will equals to 0.62 over 2 times 0.43 over 2 divided by 0.13 over 2 and then 0.56 over 2. Right, that's your Q, right? Any questions so far? No questions? I have a question for you. The Q is QC or QP? QC, right? Therefore, you want to compare the K is KC. Okay, so you cannot just compare this number to the KP, right? So they are different things. Okay, so can you actually figure out what your, this is like a QC, right? Can you know your KC? Can you know your KC? You can, right? Because we know that KP is equals to KC times RT to the delta n's power, right? What's the delta n here? 0, right? So the delta n was calculated from where? Right? So if you look at your equation, how many more of gas molecules show up in on your product side? It's 2, right? So 1 CO2, 1 H2. So you have 2 moles for your product side. For reactant side is also 2 because you have 1 mole of CO and 1 mole of H2O. Therefore, your delta N is 2 minus 2. Okay? So it's going to equals to 2 minus 2, which is 0, right? Therefore, you know your Kp is going to equal to your Kc times RT to the 0th power, which give you a value of 1. Therefore, you know your Kc and Kp is actually the same in this case. Okay? And then they will give you a value of 2.7, right? Okay. Then you go back to here and recalculate your QC. Okay, if you do this calculation, you got a value of 3.7. Okay, therefore you know your QC is larger than your KC. Therefore, sorry, you have too much product. Therefore, move to the left side, right? To the reactant side. Okay. So there are a few terms in these questions, right? Mainly it's actually you need to know when you compare your K. Okay, make sure it's actually the same K. Okay, KC can only compare to your QC. KP only compare to your QP. Okay, so you should know the term that you use to calculate your Q, is that a pressure or it is concentration? Okay. And here, another very important thing for this question is actually you should know that all the numbers, okay, that show up in your I, that's a number you can use for your Q, right? Only a number in the equilibrium can be used for your K calculation, even though the mathematical equation, they are the same. The Q and K is actually the same, right? But the number you can use to calculate this for your Q, right? That's for your K. Okay, so don't get the things mixed up. Okay, but let's see actually how you solve these questions. Okay, any question for this? Delta N is actually looking the overall reaction. This, right? This guy. So delta N is this guy, coming from this guy, right? So calculate the mole of gas molecule and only gas molecule. Okay, so you're looking for the subscripts contain this G. Okay, that's actually indicate the species is in the gas form. Okay, then you start to actually count the coefficient sum of all the gas. So in this case, the product is going to have two, right? Because one CO2 gas, one H2 gas, overall you have 2 mole of gas on the product side. Then you do the same thing for your reactant side to calculate your delta N. Okay, so you're going to see also 1 plus 1. This one also give you 2. And the delta N is actually always the product minus your reactant. Okay, that's 2 minus 2, therefore you got a 0. Is that clear? No. So you only look at the equation. Okay. Any other questions? Okay, next question then. Number 15. At a certain temperature, Kp for the reaction N2 plus 3H2 give you 2NH3 have the value of 784.8. Calculate the value of Kp for the other reaction. Okay, so this is actually a very standard type of question to calculate the new equilibrium constant K from a known equation with a known K. Okay, so the basic idea is actually if you flip the reactions, then you put the -1 power to the original K, right? If you multiply the number, then put a number at the exponent on the power of the original K as well. Okay. If it's actually an addition of two equations, then the new K will be the product of the two base equations, right? So those are the things that we talked about previously. Okay. So the things is actually want to know the new equilibrium constant for the target equation. Data that you have is N2 gas plus 3H2 gas. They give you 2NH3 gas. The Kp equals to 784.8. Okay, so that's actually the only thing that you have as the data, right? And you want to calculate the K for this. Right, so that's actually the things you want to calculate. Okay, so I call this one as my target equation. Okay, and then this is actually my base equation. Okay, so if you look at these two, they will look actually quite similar. Okay, then you want to actually figure out, okay, what's the difference between the top and the bottom? What's the target and the base? What's the difference between the two equations? Okay, what's the differences? You should see the coefficient is different, right? So basically, it's actually you multiply 1/2 to the original base equation, you'll go to your target equation, right? Therefore, you know all the operation in the coefficients will happen to the original k to its power, right? Therefore, it will be 784.8 at the square root of that. And then you're going to get a value of 28.02. And that will be the answer. Okay. Any question for this? So if I flip my target equation, if I do this, okay, then the k for this specific direction will become the original kp to the negative 1/2 power. Okay, if I flip this, okay, if we compare this one to this, it's actually I multiply 1/2. I also flip the direction, therefore I multiply -1 as well, right? And all those operation goes to the exponent of the original k. Okay, so those are the questions that you probably will actually encounter in your midterms. All right, so let's actually how you solve question number 15. Okay, question number 16 says phosphorus pentachloride decomposed into phosphorus trichloride and chlorine gas at elevated temperature by the following reaction. So these actually are reactions. Okay. If the Kc is 2.9 at 300 K, what's the value of Kp at the same temperature? Okay. So this is actually a very standard Kc, Kp conversion. Okay, because it gives you one equations, right? And it tell you the Kc and X for the Kp. Okay. Then you know the equation you should use is Kp equals to Kc times RT delta N, right? Okay, so what's delta N? Okay, the delta is 1, right? So the delta N is actually the mole of gas of your product minus mole of gas for your reactant, right? So your product has 1 plus 1, right? You have many mole of gas for your product. For your reactant, you only have 1. Therefore, you know that delta N equals to 1. All right. Is everybody familiar with this concept now? Can you actually calculate this one correctly? Okay. So once you know this, the next thing is actually temperature, right? Which R you should use? 0.082, right? Because it's involved gas now, right? So 0.082 is the things you need to use. Temperature, it's 300 degrees C, right? But you want to convert into K, right? 300 plus 273, that's 573 K. Okay, so once you have all this information, then you know your Kp was simply equals to Kc is 2.9, right? Times R is 0.082, T is 573 to the first power. Okay, so if you do that calculation, you'll be able to get a number of 136.4. And that will be your answer. Okay, So that's actually how you really do this Kp, Kc conversion. Okay, so this is actually the first example that I show you that the Kp and Kc, they are actually different, right? Because in the old example we give in the past, the delta n is always equal to 0. Therefore, your Kp is always the same with your Kc. Okay, but this one is actually the one that Kp and Kc, they are not the same. You need to know how to actually do the conversion properly. All right, so let's actually question number 16. Number 17. At 700 K, the reaction below has a Kp of 54. An equilibrium mixture at this temperature was found to contain 0.672 atm of H2, 2.99 atm of Hi. Calculate the equilibrium pressure of I2. Okay. Keyword here is equilibrium okay, right? That tells you it's actually standard chapter 12 type of questions. Okay. And then the Q that you should have is you want to know the pressure of I2 when it is actually at equilibrium. Okay. At equilibrium is actually a very important concept because it tells you you're actually looking for the value at the third row, right? The row that shows equilibrium, right? That's the things you're trying to solve. Okay. Then data that you have, first write out the equations. Okay. And then you know your Kp is going to equal the pressure of your Hi, the seconds power, over the pressure of H2 first power, I2 first power, and you have a value of 54. Okay, so let's count the things you can actually write out first. Then put down the ice. Okay, then we read the questions again, right? So it says you have 0.672 atm of H2, 2.99 atm of Hi. Okay, where should I put those numbers? Which row should I put it? ICOE. E. Okay, how do you know it's E? Yeah, because it says equilibrium, right? You see that equilibrium mixture tells you the number that they are actually providing is already at equilibrium. Okay, therefore you know you should put 0.672 for your H2, 2.99 for your Hi, right? What's the things that you don't have? It's the pressure of I2, right? At equilibrium. And that is actually the things you're trying to solve. Okay, therefore you can put X over here. Okay, so once you see all this value is in the equilibrium row, you can plug it into your Kp, right? Because your Kp is going to equals to Hi pressure 2.99 square, H2 0.672. Pressure of your I2 is unknown, but you know if you do this calculation, it gives you a value of 54. Okay, then you get to this very simple equation. Then you can solve your X. Okay, will equals to 0.25, and there will be actually the pressure of I2 at equilibrium, right? So there will be actually the answer you're actually looking for. All right, so I want to keep emphasizing that only the number in the third row can be plugged into the equilibrium equation and made it equals to your K. Okay, If it's any number in your first row or the I row, then the things you calculate is your Q. Okay. All right. Any questions for this? If not, then question number 18. At a given temperature, 4.86 atm of H2 and 3.88 atm of CO2 are mixed and allowed to come to equilibrium. The equilibrium pressure of HCl is found to be 1.239. Calculate Kp for the reaction at this temperature. Okay. So again, you see the keyword equilibrium already, right? Therefore, you know it's chapter 12 questions. Okay. And it gives you a bunch of numbers. Right. Then the things you really need to do is actually make sure you put the number in the correct rows. Okay. So the things that you want to calculate is Kp, right? That means you need to figure out all the numbers on the in the third row, right? Or the equilibrium row. You need to actually get all the numbers so you can actually calculate the K. Okay, so let's actually go. Okay. Data. Okay, write out your equation first. H2 plus Cl2. They give you 2HCl. ICE. Okay. K is going to equals to HCl second power, H2 first power, Cl2 first power. All the number we put over, all the number we put later on will be the number show up in the equilibrium row, right? All right, so now we're going to actually go back and start to put in the numbers. Where should I put this 4.86? Which row should I put? Initial. How to know is initial? Yeah, it says allowed to come to equilibrium, right? Meaning it is not at equilibrium. Everybody get this? Yeah, those wordings matters. Okay, therefore I know I should put 4.86 here. Okay. How about that 3.83? It's the same, right? It should be here, right? How about the value of 1.239? That should be put in the third row, right? Is equilibrium, right? Because it says, specifically says the equilibrium pressure of HCl, right? Therefore, you know, you cannot put it here. You should put right here, 1.239. Okay. So that is actually the setup that you have. Okay. And in order to calculate your K, that means actually you want to get this value. You want to get this value, so you can use these three. You can use these three values to compute your K, right? So that's actually a logical flow. Okay. So how do you go from the I to E? Is that you actually start to assume there are certain changes. Okay. But before I do that, what's the value here? 0, right? Because in the beginning, you don't have the product. Therefore, you know, here is actually 0. Okay. So in order to actually get the number from your row I to row E, we need to actually say your reactance is going to decrease by X. Okay. Since your H2 decreased by X, your Cl2 will decrease by X as well, because the coefficient, they are actually the same. It means actually they consume the same moles, okay, of H2 and I2, right? So if you assume I decrease X for your H2, then it will decrease the same mole for your Cl2. Okay. How about this? plus 2x. Okay, how do you know it's actually 2x? Because the coefficient is actually 2 HCl, right? You have to know if you decrease by 1 mole, you can produce 2 mole of HCl. That's why you write plus 2x over there. Okay. Then you know your I plus E will give I plus C will give you E, right? Therefore, you know this guy will equals to 4.86 minus x. This guy will equals to 3.83 minus x. This guy will equals to 0 plus 2x. They will equal to 1.239. Okay, and this is important because this equation allows you to figure out what the x is. Okay, so you can actually solve your x. So your x is equals to 1.239 divided by 2. That equals to 0.6195. Okay, so once you have that, you can plug into this and that. Therefore, you can calculate the pressure of your H2 at equilibrium will equals to 4.86 minus 0.6195. That give you a value of 4.2405. The same for your CO2 at equilibrium will equals to 3.83 minus 0.6195. That give you a value of 3.2105. Okay, and you also know the concentration or pressure of your HCl. Then you use these three numbers to calculate your K. Therefore, your K is going to equals to 1.239 squared over 4.2505 times 3.2105. Okay, so if you do like calculations, you will be able to get a value of 0.113, and there will be your Kp. Okay. So again, this is actually the question that requires you to really know where to put your numbers. Okay. Okay, any questions for this? A little bit louder, I cannot hear you. No, because the things you use is always the pressure, right? This is Kp, right? Yeah, so it already give you the information about the pressure already. Okay, so it doesn't actually just give you the weight of the substance. It actually give you the pressure already, which is the things you need to use to calculate the K. Okay, but if today is actually giving you the mass of the substance, then you need to actually first figure out the formula way to get the moles. Okay, and then divide it by the volume to get the concentration. Okay, and then you can go from the concentration to the pressure afterwards. Okay, so that's the differences between this setup and the things you're actually asking. Okay, any other questions? Okay, if not, then let's go through the question number 19. Nitric oxide react with oxygen to form nitrogen dioxide following this equation. Okay, what is Kc for the forward reaction if equilibrium concentration of NO is 0.2, O2 is 0.1, and NO2 is 0.25 m at 25 degrees C? Okay, so you see it asks you to calculate the Kc, right? So apparently it's actually the chapter 12 type questions. Okay. The Q that you want to compute is Kc, right? the data that you have is what? 2NO plus O2 becoming 2NO2. Okay, so every time you see this chapter 12 type question, when you set it up, put the eyes here, right? So you know you put the number at the correct location. Okay. So you have this value, 0.2 for NO, 0.1 for O2, and 0.25 for NO2. Which row should you put these numbers? Equilibrium. Okay. How do you know? It says the equilibrium concentration, right? So that you know NO is 0.2. O2 is 0.1. And then this one, NO2 is 0.250. You actually calculate what? Kc, right? So Kc can be calculated by the concentration of NO2 squared over NO squared O2 first power. Okay. Since it's actually asking the Kc, therefore all the information you need is actually the concentration, right? And then when you look back to the questions, see, you use this M, right? Capital N, right? I mean, that's actually the molarity. It's already a concentration term. Therefore, since it is actually in the equilibrium role, you can just plug these numbers in, right? So 0.25 square over 0.2 square, and then 0.1. And by doing that, you'll be able to get a number of 15.6, and that will be your answer. Okay? And that will be the very last question we want to go through today. Yeah, we made it. Okay. So the things that you need to do further, okay, you should actually go back, first go through all the questions we went through in the in-person lecture. That's always the number one thing. Okay, and then try to understand my logic. Okay, how I actually approach the questions. Read the question carefully. After you have done that, the next thing you should do is actually get the old questions from the ACS chapter. Okay, and then during the weekend, do the practice exam. Okay, then you should be good to go. Okay, so I hope this is helpful. Okay, and good luck with your midterm one.